Okay, now I'm recording, and you can share if you don't mind the show result. So very good, Maxi.
Okay, it's here.
Okay. Actually, one can do this plot. You have done it because you solved the equation, but it is possible to do it without solving the equation, applying simple graphical rules. That's the so-called root locus method. Okay. So you have branches, and you have rules for the real part that belongs to the possible places where you have closed loop poles for some gain, and you have two branches that go to infinity in this case. In this case, you increase the gain, and then it always becomes unstable. So can you understand what happens? Suppose that k is very small. Suppose that k is very small. What happens to the type of response that you get? Remember that these poles are the exponents of the exponentials. So if you have a very small gain, where do you have the poles? Can you use, say, a blue ink and mark an example where you have approximately poles for k small?
I can't change the color. I don't know why. Doesn't appear the option.
That's good, because you know how to solve the problem, but you don't know how to how to change the color. I
No,
don't bother about the color.
yeah, I don't know. It doesn't appear. Yeah, it isn't here now.
It disappeared.
Yeah.
Okay. Anyway, so you
So when
make
K
a
is
square,
small,
make a square to mark two poles for k small, more or less. So a typical situation with small gain.
with small gain, and when the system is stable, right?
Uh, probably when you have one unstable pole and a stable one. So mark two squares there, two small squares. You will have one in the left and one in the right. No? Advance a little bit more.
Something
Okay,
here
something like
and
there.
here.
Can you make a small square there, for
I think
instance?
so. Uh,
Okay, one there and one there. So what type of response do you get? Does it oscillate? Does it go to zero? Does it go to infinity? Does it not oscillate? Do you have oscillations in this situation?
so the imaginary part is 0. So I would say no.
Okay, you don't have any the imaginary part is zero, so you don't have any oscillation. Do you go to zero?
No, because we have this one over here, which is positive.
And goes to infinity. That's what. So you go on, increasing the gain, and there is a situation in which both poles are negative. So can you mark with a triangle two poles in this situation in which you have both poles uh, with negative real part, say one there, and one symmetric with respect to the, actually you can show it symmetric with respect to that point. Okay, so in this case, what happens? What type of response do you have?
I'm sorry, I didn't understand. So this one is here for a given
Yes,
K?
and you have another one which is on the other side of the, if you do the computations, you can show it is symmetric with respect to that vertical green line.
To the, okay, to this one. So it will be here?
More or less there, yes.
Okay, okay.
Okay?
Yeah.
So if you do the computations, you can see it's symmetric. So in this case, in the triangular case, what type of response do you get?
I would say it's stable, so something that decreases.
That decreases, goes to
And
zero.
goes
But
to
now
zero.
we have the reference, okay? So it will approach the reference without oscillating. The reference is a kind of zero, no? Or it will approach, if they don't approach the reference, they will approach something which is a reference multiplied by a constant without oscillation. Now you increase more the gain and the two poles collide with when you have a double pole. Okay, and if you increase it more, you start having imaginary. So suppose that you increase the gain and you get the round points.
Yeah.
What type of response you have for the round points?
It goes to zero, but with oscillation.
Oscillates. Okay, so it goes to the reference oscillating. Okay, now increase more the gain and you have, say, I don't know, put a star or something.
Something.
See, yes, something there. And the other is symmetric. The other is symmetric. It must be symmetric because the polynomial, the characteristic polynomial, has the coefficients of the polynomial are real. So you must, the roots are complex conjugate. So in this case, what happens to the response?
It's similar to the other one.
So it oscillates and it's stable.
But the oscillation would be the similar to the previous one, or would be more oscillation?
What do you mean by more oscillations?
So I mean like the turbulence also. But if there is any difference or no? I mean it would be the similar.
There will be a difference. There is one difference that you probably can see. It's faster. The oscillation is faster, and probably the amplitude will be bigger. The initial amplitude will be bigger, and the oscillation is faster. Okay. You have the velocity of the oscillation depends on the imaginary part, the frequency of the oscillation, better to say. Okay. Let's do some simulations. Let's do some simulations to test our theory. Before we leave this, any question? Okay, let's do. So, Imaxi, if you don't mind, can you release the screen? Okay, so let me go. Let's go to Simulink, and I must share. So can you see my Simulink window?
Yeah.
Okay. So let's create a project. How can I create a project? Well, I must click here and here. No, sorry. Here. Let's go to the continuous. Where do we have the continuous? Library. So I have.
Hello.
Hello. So we have a transfer function there. Not sure whether that is what I want. Okay, is this one? So 0 pole. And I have no zeros. So this is void. And I have poles at 1 and -3.
Okay.
1 and -3.
So this is from the homework, right?
No, yes, we are exploring that stuff. Okay. So this is our open loop transfer function. Now I want to do a feedback. So I pick up math operators, math operations. Where do I have math operations? Math operations. And a sum. I will need it. Let's put it here, here, and again. And then I do a feedback. But this is not a summation, it's plus minus. Sorry. Let me place it round. And I think that this is okay. Okay. Now we need a source and signal generator. So I'm using a step. Unit step. And now I want to see what is happening. So I go to the sinks and I pick up the scope that I place here. Okay, for a fast simulation, this is okay. So I open it. I want to configure, so model configuration parameters. This is the time. So I will increase the precision to 6. And the stop time is that one. And everything disappeared. I don't have it anymore. Where do I have it? I have it here. Okay, you can see the block diagram. And also, now our theory is that for small values of the gain, you get an unstable system. So let's see, and the critical gain, did you compute the critical gain? Let's try with 1 to see what happens. Nothing happens. Or running. The first one, he has to interpret it, so it takes some time. Just they are checking everything and everything and everything, so the newer the version of MATLAB, the longer it takes. Actually, it's taking longer than I expected. I don't know what's happening here. Oh, I see, I see. I must save it. Sorry. It crashed. I should have saved it. Okay. Oh, this one. And this other one. Well, it was going, you see. It was going as an exponential, as expected. So let's save this. Okay, this is not probably, let's call it test. Okay, so now it's, you see, it's going. Now, let's increase a little bit the gain. Let's use, say, 2. Still unstable. Now use 3. Still unstable. Now use 4. Or 4, yes. Okay, now it's stable. And it does not oscillate. Let's do a longer simulation, say for 20. Okay, so you have this type of response that does not oscillate. It does not go to 0. now the 0 has been shifted by the reference, by the fact that you have the reference. Now, what happens when we increase more the gain? What was our theory?
It will go to the reference, but there will be oscillation.
There will be oscillation. So let's place, say, 6. Okay, some very, very damped. But now let's increase even more the gain. Say, let's place 20. Okay, you see? Now place a very high gain, 200. So 10 times more. Okay, and the oscillation you see is becoming faster and faster. Let's do it only up to 10 so that you can see it. Okay. Now, or let's do it up to 6. Okay. Now let's increase the gain. Instead of having 200, I put 2000. It's much faster. The frequency becomes higher. Okay, because the imaginary part is increasing, the real part is the same. You see that the damping is more or less the same. Actually, is the same. But the frequency of oscillation is increasing. Why? Because the real part is constant and the oscillation and the imaginary part is increasing. Okay? So we could have said, instead of specifying K, I could have specified, I want the poles at some place. Okay? I want the poles at some place. But I only have one gain. So with this gain, I can only change the poles according to that cross. No? They come one to the other, and then one goes up and the other goes down. Okay, so a possibility is that we have access to the state. So instead of considering that we have just a transfer function, we have the state. You remember the story of the state matrix? Linear state model? I'm sure you don't remember, but I pretend you do. Okay, so let's go to the whiteboard. Let's go to the whiteboard. So where is the whiteboard? The whiteboard is here. So stop sharing. Oh no. I must open it. Okay. Now, suppose that you have one system which is a kind of integrators. Remember, let's do something which is very, very simple, has nothing to do with biology, but it's just is just something that everybody understands. So I have a mass with a force U, and my mass is 1, and this is sliding along the action, which is Z. So M, which is 1 Z dot, ZW dot, is equal to the sum of forces, which is U. Okay? And this is equivalent to say what? This is equivalent to say that X1 is equal to Z. That's the position. X2 is equal to Z dot. That's the velocity. So I have a block diagram, which is something like this. Now, use the equations are what? So x1 dot is Z dot, but Z dot is x2. So x1 dot is x2, and x2 dot is ZW dot, which is U. Okay, so these are my equations. Now let's use the S stuff. If you use S, you say that x1 is what with respect to x2? S means the derivative. So x1 dot means sx1. So x1 is what with respect to x2?
X2 divided by S.
So 1 divided by S at x2. No? And x2 is what with respect to U?
One divided by S. U.
1 divided by S. So I prefer to do it like in this way because I have my signal and I have something that changes the signal. I call it an operator. Okay, and instead of having, I mean, mathematically, if I write x2 divided by S, it's the same. But I prefer to separate things. So if I have U, then U is transformed into x2 by 1 divided by S, right? And x2 is transformed into x1 by 1 divided by S, okay? Now, instead of feeding back x1, let's see what happens if I feed back x1. So let's start experimenting our wings. So I put here a K. Plus, minus, and the reference. And then I do a feedback. Okay, so if you want to think about a simple model of this, it's something like, this is something like, instead of that silly object that slides, it's something like you have a coil, and you have an electrical signal here, and you have a magnet, and you have a iron core. So this is iron, ferro, okay? So you create a magnetic field, and now you have a small sphere, okay? And due to gravity, the sphere comes down, falls down. But due to the magnetic field, it goes up, so you can equilibrate, okay? And to equilibrate it, what you do, you put a light source here. A light source. And you put a light sensor. Okay, so this is a light sensor that somehow measures the interruption of the light by the sphere, so you can measure the position. Okay. Now, what am I doing? I'm doing something like I measure my position from the light sensor. I have a desired position, R. So this is my plus minus. I have a differential gain that I can do easily with electronics. So I have here some K. And I have some electronics, some power, probably I will have some power electronics here, power amplifier to give me enough current so that I act on the force. You see, as simple as this. So if the sphere is going down, it interrupts the flux of light, and this means that the position is below R, so you have a positive error, you increase the force. Okay? Now, does this work? I mean, does this work in the sense that it should be stable and it should lead the sphere at least to some position, maybe not in R, but a little bit above or below? What do you think? What can we do to study whether this stuff works? Now you have a tool. You can write a book about S stuff. By K. Ramani, H. Narotano, and J. Basilio. So everybody will be asking about your book. Say, have you read the book by Ramani, Narotamo, and Basilio? Oh no, I haven't. But it sounds nice by looking at the names of the authors. Okay, the S stuff. My adventures on the S stuff. Okay, I see that Jose is taking careful notes about this because this will be part of the exam. So we are equipped with the S stuff. Sorry to cancel your names. This is the first step for glory and fame. You know that one day, many years ago, I don't know, I was 23 years old or something. I was at an industrial fair, and I was at a stand selling equipment for teaching. I mean, electronics and control and kits for teaching. And I was there showing the equipment and speaking about the equipment and so on. So a guy came to me and said, well, I'm an inventor. I asked him, well, but what do you invent? And he told me, I don't know, I haven't invented anything, but I want to invent something that brings me fame and glory, okay? So I had to do a very strong effort not to start laughing in his face, but I reach it. Okay. Now, about fame and glory. What can you do with your stuff to see if this device will work?
Write x1 as a function of r.
That's very good. So x1 is equal to r, and if I had not told all these silly stories, you would not have answered. So, and now, here, remember the story that if I have A, and then a feedback with B, with a negative feedback, this is equivalent to A divided by 1 plus AB. Good. So here, what shall I place on the top?
Okay.
K. And then what is A in this case?
K divided by a square.
K divided by a square. And here, if you don't tell me, I won't write it.
1 plus K divided by a
1
square.
plus K divided by a square. Okay? And this is x1 equals to K S squared plus K R. So where do we have the closed loop poles? I'm going to look at which equation?
S squared plus K.
S squared plus K equal to 0. Okay. So what is the solution? S12 is what? So S squared is minus K.
Plus or minus square root of Kj.
Of J square root of K. Good. I'm assuming that K is positive, because if K is negative, it won't act in the same way. So it would instantaneously become unstable. So what is your conclusion about the movement of the sphere? What is your conclusion about the movement of the sphere? Does it stabilize to some point? Does it become unstable? Does it oscillate? But the oscillation is damped, is dying? Does the oscillation grows? Does the oscillation keeps constant?
I would say it keeps constant because
So
the
it's a
real
constant
part is,
oscillation because you have, why is it a constant oscillation?
the real part is 0.
So you only have an imaginary pulse, pure imaginary. So you have, so the sphere here would be oscillating without endless. Okay. So you would not be able to keep the sphere constant. Let's see let's do a simulation, a numerical simulation. So let's stop sharing. And then I share again this stuff. You can see. Oh, I'm sorry. What I want to do is a different thing. I want to share this stuff. Now you can see the graph and what we have done before. Não? Conseguem ver o bloco Simulink e a simulação?
Sim.
Certo. Okay. So let's change this. So now instead of having this system, I clean it up and I pick up two integrators. I pick up two integrators. Where do I have my integrators? Oh, it's here. So continuous integrator. So I connect. Okay. And then I need another integrator. I replicate. Good. So in the end, I have the position, and here I have the velocity, and here I have the applied force, and this is the gain. And this is the feedback. Okay. And let's look at the initial conditions for the integrators. 0 and 0. So 0 initial position, 0 initial velocity. So let's use a gain instead of 2000, use a gain of Christian gain of 4. So we save it and fuga peça. Okay, you see the oscillation. So instead of just doing this, you do a simulation up to 20. It's oscillating. You see, never stops. Now change the gain. Use a lower gain. Use a lower gain. Say a gain of 0.1. What do you expect to happen? It's a positive gain. And the eigenvalues of the closed loop were plus or minus j square root of k. So when you reduce k, what happens?
Lower oscillation, probably.
Slower, mais lentas. But still oscillating. Okay, slower oscillation. So let's do up to 200. Okay, it's oscillating. Now you go to 200, but it's, I don't know, 10 times slower. Now, if I increase the gain, what happens? Still oscillating. So instead of 4, I put 20. But now they are faster because your imaginary poles are further away. You see, it's oscillating very fast. Okay, it's a very fast oscillation. So our theory predicts what happens with the simulations. Now, questions. Do you want to make questions? You don't want to make questions, but I want to make a question. How can we change our control system? So let's go to the whiteboard again. So how can we change our control system such that you stabilize the position? Any ideas? Perhaps buying an extra sensor. What I'm going to do is, instead of putting the gain here, I'm going to feed back the position, but the velocity as well. Okay. And so I will have two gains. So this would mean that I would be measuring the velocity. I would have some sensor of velocity. Maybe I could differentiate the light signal. I don't know. I'm going to cancel this thing here, but you should be aware that you have a physical thing that you can model as a block diagram. And this does not only apply to, in this case, it was a kind of electromechanical system. You have mechanical parts, the sphere and the magnet, and the electronic part. Okay, you can do everything here with electronics. Actually, once you were doing this like that, all the control systems were done with analog electronics. Now you don't. You do it with a computer. You buy an Arduino for €4 in China, and you program your controller there. And the Arduino already has AD and DA converters and everything there. Okay, and you buy sensors for €3 or €4. So by less than €20, you have a whole system to show to your friends. But be aware, have conscience that the block diagram represents a real thing. It's not just a game. Okay, it represents a real thing, and you can then use it to do simulations. Any question? Okay, so let's modify our controller. So I will clean this. I will clean this stuff to gain space. Also, I will clean this stuff and this stuff. And let's design our controller. So in red, so I pick up the position. There is some sensor measuring the position, and I multiply this by some K1. Then I pick up the velocity, and I put a K2 here, and I add. And this is plus. And then I feed it back. Okay? Now, again, I want to express x1 as a function of r. But of course, I can start writing equations and eliminating variables and so on. But there is a trick that we can do. And the trick is this. So let's withdraw this in an equivalent way, such that we can apply that rule of the feedback. So I have 1 divided by s. I have 1 divided by s. And I have the K1 that receives this, okay? And I have a summation point. A summation point, and it sums there. And I have K2. and it sums there. Okay. Now, if I pick up this signal and put it there, it's the same as I had as before, only with the difference that now the drawing is different. But if I write this, say, if I do something like this, both the diagrams are equal. You agree? Now, let's do a change. So instead of picking up the signal here, I'm going to pick it up here. But I want this to be the same signal. I mean, the effect should be the same. So what shall I do? I have my wire that should come here, but I'm picking up there. So I must multiply by the inverse of this transfer function. This transfer function is 1 divided by s, so I should add an s here. And this is equivalent. You understand? The point is that since I'm not picking it here, I'm picking the signal here, and the signal here is what? Is 1 over s x2. But I want to feed back x2, so I multiply by s instead of just keeping k2. I have k2 times s times 1 over s x2. So k2 s 1 over s x2 is the same as k2 x2, right? Okay. Now I have 2 blocks in parallel. So I'm going to replace these 2 blocks in parallel by their sum. So I would say that these blocks in which x1 enters, so let's clean this stuff here, is the same as k1 plus s k2. Okay, so I'm going to replace these red blocks by a green block that picks up this signal and multiplies it by k1 plus sk2. And I have an equivalent thing. So I cancel this stuff here. And now I have something which is k1 plus s k2. Okay? So let's clean this stuff.
What's me? What's me? What's me?
Faça um favor.
What's me?
Okay.
It's open.
Now you can compute the transfer function between r and x1. What is the transfer function between r and x1? Is x1 equals to, and then in the upper floor, no primeiro andar,
1 divided by s square.
and in the lower floor, it's a loop gain.
1 plus
1 plus
1 divided by s square times k1 plus sk2.
okay? And you can say that x1 is 1, and then you have s squared plus SK2 plus K1. Now, remember what was our motivation? Our motivation was to have a control system that allow you to impose the closed loop poles. Okay? So I say, what are the eigenvalues, the K1, the values of K1 and K2, such that the closed loop poles are, now tell me something reasonable. What should be the real poles?
-4, -1,
-1 and
-4.
and -4. Okay. What is the rationale for your desire?
We want the system to be stable. And
Okay.
if the real part of the poles is negative, it will be
Okay.
stable.
And you don't want any oscillations because you are against oscillations. That's good. So it will go there. Okay. Now, how can I solve this problem? How can I solve this problem? Can I clean this part here? This part was just a trick, you see. You move all these intermediate branches to the right, and you get a standard feedback form. So this was just a trick. The real block diagram is that one. Now, how can I design, how can I select K1 and K2 such that the poles are at the desired values?
We can write the expression of the poles.
You mean a polynomial that has these roots, -1 and -4. So what could be a polynomial such that, so the desired characteristic polynomial okay? So it's a polynomial that has as roots -1 and -4. So what could it be?
S square.
Maybe S square is asking too much before coming to the S square.
S plus 1 times S plus
S plus 1 and S plus 4, because in general, if you want a pole to be at beta, you get S minus beta. Okay, and this gives you a root at beta. So in this case, you have two terms, one at -1 and one at -4. So you have S minus -1 and S minus -4, right? And now you expand it. Okay, you expand it. Let's expand it. So this gives what? S squared plus 5S plus 4, isn't it? Okay, and now?
Now we have to make equal to 0, no?
Okay, so
We make
should
the
be equal to
quadratic
0.
function.
But to find K1 and K2, don't forget what is our problem. this is what the characteristic polynomial that you get by selecting K1 and K2. And you want this polynomial to be this one. So what do you do?
K1 is 5.
K1 is what?
4.
4?
And K2 is 5.
K2 is 5. So in this case, it's very simple. Just equate the corresponding coefficients. Okay? In this case, gives you immediately the values. So K1 is 4 and K2 is 5. So let's see what happens to our control system. Now we don't have this. We are going to have some, so we disconnect this from here. And we disconnect this from here. And we set this gain. And we connect this to here. Okay, that's the error. Now, let's put the gains in the vertical. So I do rotate and flip. Rotate clockwise. Okay. And I need another one like this. Gain 1, and if I do it again, I get, oops. And if I do it again, I get a K2. Then I come here and I close this one. So I get K1 that multiplies by that value, and the value should be 4. And I also have another one that should pick up the velocity. So there should be some sensors here that I'm omitting. And I also need this summation point. So again, I do some flipping here. Okay. So okay, and this goes there. And this gain should be 5. This gain should be 5. Okay, now the grand finale, let's see if it works. Where do I have my scope? It's there. Let's see if it works. Okay, so let's simulate it for just 10. Okay, and you, okay, so you were at 0 and you went to some value. Now, the step has a value of 1. So this should go to 1, but it goes to 0.25. Now, If I wanted it to go to 1, maybe a simple way is to multiply this by a factor, which is so let's pick up instead of flipping and flipping and flipping. Gains, math operators, gain. I multiply this by 4. And then now it goes to, this is a 0. There is something that I don't like. Maybe there is some initial condition. 0. 0. Okay, now it goes to 1 and it's stable. Okay. And you could change the specifications of your poles, for instance, to make it faster or slower in responding. Okay. Or you can say, I want, suppose that another experiment, I start with 0 initial position at position 1. So I put 1 in the initial condition for the position, and I put 0 on the step. So nothing is coming from the reference, okay? But you are stabilizing things. So you will decay from 1 to the 0 position, which is the reference position. What's happening here? There is something plus plus minus. Why is this starting at 1? Let's disconnect this stuff here and put a 0. Constant. Zero. This is okay. I really don't know what's happening here. Okay. For some reason, this was not working. Okay. So you start you start at a position 1 and you go to 0. Okay. So you had some, you deviated, you go there and you blow a little bit so it moves and it goes to 0. Suppose that you start at position 1 with velocity, with some velocity. So you add here some velocity, say 0.5 or 0.2. So initially it was at position 1 moving up, and you want to bring it down slowly to 0. Okay, it has some overshoot. Let's do it a little bit more pronounced. So suppose you have a velocity of 1. Okay, you see that it was going up, but your controller brought it down slowly, smoothly. And this has no oscillations. Why? Because Emaxi specified negative real poles. If she had specified poles with some imaginary part, with a negative real part, but with some imaginary part, then there would be some oscillation here around 0. Okay? So what is important here, there are many things that you are seeing here, but one main point is that position and velocity are the state. By feeding back the state, you can place the poles wherever you want. At least in this case, it was so. In general, there is a theorem that says that provided that your controller has some meaning, I mean, if you want to control the temperature in the room where you are, you don't put a heater in the house of your neighbor. Okay? And there is a mathematical counterpart for this. I will later tell you what is the mathematical translation of this fact, that you should have your actuators well placed. If your actuators are well placed, you can, by feeding back all the state, you can place the closed loop poles where you want, and not just in certain positions as you get by feeding back the output. Okay. Later we will see that we can change things. We don't need to stabilize, to feed back the state, because we are going to estimate the state, but that will be another story. Questions?
No.
So you are speechless.
Yes.
Okay. So have a nice weekend.
Just one question. In the beginning, so when I came late, did you correct the homework, or you didn't do anything?
Yes, Emaxi did a presentation.
Okay,
Emaxi did a presentation.
Okay, can I ask just one thing? Was S1 equal to 1 and S2 equals to -3?
It was more complicated than that, because the idea was to consider different values of K.
Okay.
Okay, and when you for low values of K, you get always an unstable pole. For K equal to 0, you get the open loop poles, and one pole is unstable. And then you start increasing the gain, and the poles start, one is a stable one going to the right, and the unstable one goes to the left. There is one moment, so one value of K for which both poles are both real and in the left half plane. And then you have a double pole. There is a value of K, which is K equal to 4, I think, for which you have a double pole, that is to say 2 poles at the same position, at position -1. And then the poles start becoming imaginary with a constant real part, which is -1.
Okay.
And one moves up and the other moves down.
Okay.
So it's much more complicated than what you are saying.
Yeah, it sounds like it. Okay, so I'll then check the video for the beginning.
Okay.
Okay.
So
Thank you.
have a nice weekend.
Okay,
Thank
thank
you.
you.
You too.
Bye.
Bye-bye.
Bye-bye.
Bye-bye. É agora às 7? É às 7? Passam 7 horas. Já vamos já ligar. Espera aí. Por acaso estava esquecido. Epá, não é amanhã. Não, pá, bolas, pá, é dia 6, é amanhã. Vamos lá ver. Mal. Histologia. Dia 6 de maio, pá. Amanhã. Boa.